Hello. Hello, 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 hello. Volume, hello. All right, everybody, we're going to get started pretty soon, so grab your last drinks and seats and slices of pizza, and we'll get ready to go. All right, well, welcome to CloudFlare. This is our new office. I know I recognize some faces from, this has been probably a year and a half since we've done this, back at the old CloudFlare office, but welcome to the new and improved CloudFlare office. And if you guys are not aware of what CloudFlare does, we are a security and performance company. We help speed up websites and web services as well as secure them. One of the biggest, sort of most important things that we do is to provide encryption for these websites via HTTPS. And part of this is cryptography, and this is sort of like core to what we care about as a company. And so we started the series of talks from people who are not necessarily going to talk about HTTP and the web and HTTPS, but sort of cryptography from all angles. And our first speaker today is Brian Warner, who's going to talk about a project called Magic Wormhole. And Brian, if you're ready, let's give him a nice warm welcome.
Hey, everybody. Hey, everybody, thanks. Clicker not working again? Okay, great. Thanks everybody for coming out. So yeah, my name is Brian Warner. I work on secure communication, secure messaging storage systems, Tahoe LFS, a couple of other things. And I'm going to talk to you about a project I've been working on called Magic Wormhole. This is a file transfer system. The idea is to get something from one computer to another safely. It's on GitHub, github.com/warner/magic-wormhole. Please take a look at it. So it's a file transfer application. It is a Python thing. You do pip install Magic Wormhole. The name comes from, if you kind of imagine, if you will, two wizards that speak the same magic spell into the air. And when they see the same spell into the air at the same time, this wormhole pops up, and they can put things through it. They can put files, they can put passwords, they can put directories, things like that. On a computer, it looks like this. The program, you say, wormhole send, you give it a file name, and it says, the wormhole code is. This is the single-use peg code that's kind of the core of this stuff. You get that code to your friend somehow. You get it to the other machine. You then say wormhole receive, and you type in this code. That code is enough for the two machines to locate each other, negotiate a shared session key, find a common connectivity, some sort of direct connection between the two, encrypt the data, send it over, and make sure it got there. The wormhole code itself is the important thing to get across from one machine to another. So this feels like it should be a solved problem, right? You know, the file transfer protocol, RFC 765, is probably older than most of the people in this room. I don't even know, like, people these days probably don't even know what FTP is anymore. So what's kind of wrong with this? You know, what are the tools that we currently use? I bet, a show of hands, how many people here have had to move a file from one computer to another sometime in the last couple of days? It's like everybody, right? So, what tool did you use for that? What do you use to move files from one machine to another? Say again? Okay, somebody else. Another tool people use for this purpose. rsync, Dropbox. Okay. SCP, good. New one, another one. FTP. Okay, anybody just send it with an email attachments. Old school, right? Okay. So what's wrong with those things? I would argue that if the goal is to move it easily and safely from one machine to another, then most of those tools kind of fail on those accounts. Like if you already have a connection established, you know, SCP is a good kind of example. Once you have your public key in place, then it's really easy to send it to somewhere. If you have a corporate file share that you can just drag it to, that's also really easy. But the specific case that I'm trying to aim at is when you don't have a relationship with that other computer already. So you've got some cool cat video on your machine, and you want to get it to that person's machine next to you. How would you go and do that? So of the techniques that we have available to us, the most obvious one that I think people would reach for is attaching it in email. Now, the security of that, we can tell that's going to be pretty bad, right? It's like, if you're really lucky and you have RTLS connections along there, then you're not, then you're only vulnerable to the server that's holding the email, the certificate authorities that are providing those certificates for it, anybody who breaks into the recipient's account 2 years from now while that file is still sitting there. But for most people, you also have to include all of the network connections, all of the ISPs, everybody that can see that SMTP connection going along, because we don't have any meaningful encryption on it. And as far as ease of use, you have to dictate a string. You have to transcribe an email address. If Alice wants to send something to Bob, Bob has to say, my email address is letter, 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 and then Alice has to correctly type that in. So she has a transcription task using those email addresses. If you upload it to a web server, to an FTP server, then you have to dictate the location where they will be able to retrieve it. You have the same kind of task, but with a longer identifier. You have a whole URL to do, and all of the same network problems apply. There are too many folks out there that can see that file. And the goal is to move a computer, move something from one machine to another, not to everybody on the entire internet. The Dropbox option. Dropbox has this really nice UI where you can just hit a menu item on a file and it'll say, here's a URL from which somebody can fetch that. That URL has an awful lot of entry to it. It's a pretty long random thing, so you have to transcribe that to somebody else. That's a difficult task. Dropbox is in the trust set for that. They can see that. You might try and make the transcription task easier by putting that long URL through a URL shortener. Now you have a short URL to speak to somebody else. That's easier. However, there was a paper that came out about a week ago on the security problems when you're using those URL shorteners, where somebody went through and enumerated the entire address space of the short URL services and found all kinds of interesting documents that people thought were private because they just didn't tell anybody what the URL is, and not really appreciating that like 5 letters is not an unguessable string. USB drive, if you have physical proximity to somebody, you can hand it off to them. That's pretty easy, but it's kind of hard to delete something from a USB drive. You know, flash memory kind of never forgets. And also, like, taking somebody else's USB drive and putting it into your computer is kind of gross. Like, you know, you don't know what might be on that USB drive. It's a well-understood technique for getting around air gaps. SCP, if you have to set up the relationship for the first time, you have to get your public key onto that target machine. So that's a lot like these other transcription tasks, except with a much larger string. So I'd say all of these sort of fail on the being both easy to use and safe. And in contrast, the Magic Wormhole approach, you have a short wormhole code that you hand to somebody, and then you're done. Okay, so if I've now convinced you this is the easiest and safest way to transfer a file, then you should ask how it works. There are a couple different phases to it that I'll go over. We start by exchanging a bunch of messages through a rendezvous server. We're going to use that to agree on a key using an algorithm called PAKE that I'll go into in a little bit. The next step is for the two machines to try and locate each other, to do an IP address exchange to be able to make a direct connection. And then finally, we get to do the actual encrypted data transfer. So the reason that these wormhole codes can be so short, the wormhole code is a number and then a pair of words. And the reason they can be so short is because this is implied, it's implicitly scoped to a particular rendezvous server. So in this client, the rendezvous server URL is baked in. And when you say, I want to talk to somebody that's using wormhole code 1 liberty assume, that 1 points to a channel on that particular rendezvous server. So the rendezvous server is just a simple store and forward. I add something for channel 1, later on somebody comes and picks it up, adds something to it. The channels allow these to be two different people doing an operation at the same time, aren't colliding with each other. These systems use there. The rendezvous server, the clients end up exchanging 3 or 4 messages on them. The first message that is exchanged is a PAKE message. Now, PAKE is a family of algorithms. It stands for Password Authenticated Key Exchange. This was first developed back around the early 90s. It's a pretty cool algorithm. It allows 2 people who share a short, low entropy secret of some sort, like a password, and leverage that with a couple of round trips into a full strength key that gives you full forward security. It gives you these nice properties where somebody who is eavesdropping on the connection doesn't learn anything about what that key is. The earliest, best known example of a PAKE protocol is probably SRP, Secure Remote Passwords Protocol, which was defined in 1997. It doesn't really have a great security proof. It's not a modern protocol in the sense that it's been made to be provable or made to be something you can get some confidence in. It's just kind of stuff hacked together. So the one that we use in Magic Wormhole is called SPAKE2. This is created by Michel Abdallah and David Pointcheval in 2005. I won't go into the math in too much detail, but it's basically Diffie-Hellman key agreement, except that the factor that you send to the other side, the ephemeral public key that you use, is blinded by the password you're using. So Alice puts this blinding factor into, she blinds the message that she sends, and then Bob uses his copy of hopefully the same password to unblind that factor, that divide by u to the PW step. And if they both have the same blinding factor, if they both have the same password, then they wind up with the same key. So the core premise of all PAKE algorithms is that if you put the same password in on both sides, you wind up with the same key at the end. If you have different passwords, then the keys that come out the other end are randomly distributed and completely unrelated. Knowing one of them doesn't give you any information whatsoever about the other one. That's pretty slick. So I have a pure Python implementation of this. If you want to check that out, pip install Python SPAKE2. It runs in about 14 milliseconds, which is plenty fast for a human-oriented application like this. So the security properties of PAKE. I've seen a couple people get kind of wigged out by the fact that these codes are so short. You know, they want to think of this as a password. And what passwords need to do is to survive a longer-term attack, frequently an offline attack. In this application, these wormhole codes are single-use. They're machine-generated. So, you know, nice uniform entropy. There's not a human who's always going to say 1, 2, 3, 4. And then the fact that the attacker only gets one guess each time the protocol runs is what provides a lot of the security. So the codes that the default command line tool produce are 16 bits long. So in the code we saw before, you know, 1 essential liberty, whatever it was, the digit 1 is a channel ID that's visible on the network. Those 2 other words are coming from a word list. It's actually using the PGP phone word list, which has 256 words in it, even in odd columns. So you get 8 bits per word, 16 bits, 65,000 possibilities. A passive attacker gets no information whatsoever. An active attacker pretends to be Bob, runs the protocol. If they get it right, they have the same key. If they get it wrong, it's something unrelated. And most importantly, Alice notices that Bob didn't get it correct. So failed guesses are visible to the user, and for the attacker to have a reasonable chance of success, they have to convince the user to fail over and over and over and over again before they can get through enough of this key space to actually have a significant probability of attack. So each time, so this is what it would look like either if there was a man in the middle who failed to guess correctly, or, much more likely, your correspondent that you told the wormhole code to failed to type it in correctly. So in both cases, the confirmation message, it does the PAKE, it sends a hash of the session key, it sees that it doesn't match. It says, hey, this failed. Either you or your correspondent typed it in wrong, or an attack was thwarted. You can run it again. That'll give everybody another chance. And 16 bits is enough that a user would have to try and send this and tell the code to somebody and see this message over and over and over and over and over again before the attacker has an even remote chance of getting this. So that's why it's a really nice property, because PAKE is trading interactivity for protection against offline attacks. And that's not a property that most of the basic encryption tools that we have in our toolbox so far really do. So I like to describe it as lazy easiness helps to improve security. Okay, so once the session key is established, the two people know that they have the same key, nobody else has that, then they use that to encrypt all of their subsequent messages going through the rendezvous server. This is where it turns into kind of boring network plumbing. This is not a kind of crypto thing, but the two sides are trying to establish a direct connection so that they don't have to keep going through this rendezvous server. The rendezvous server is a little bit slow. You're definitely sending your messages off to somebody and then waiting for a message to come back. For bulk file transfer, you'd much prefer to have a direct straight-through connection. And in a lot of cases, you can do that. I don't yet have full sort of NAT hole punching stuff in place, but what I'm told is that if you do it right, then you can get maybe 80% of two random machines on the internet can get a direct connection to each other. And for a lot of the use cases of a tool like this, you know, if the two of you are trying to exchange cat videos in your machines, you're both on the CloudFlare network. You both have local addresses. It'll discover that. So it can go really fast. And then the other thing is that I run that rendezvous server, and I want people to use this tool, but I don't want to be footing the bandwidth bill if it actually gets popular. So they basically use ifconfig. They figure out what their local IP addresses are. They listen on a TCP port. They tell the other side, hey, you might be able to reach me on 10.net.something or else. Or maybe one of the machines has an external IP address, and you can reach me on that. They both get those addresses. They both try to make all of those connections. They use the session key to do an encrypted handshake on that to say, you know, prove to me that you know the session key that we negotiated over that rendezvous server thing. If that all succeeds, then they use that channel and they forget about all the others. There are cases where both machines are behind NAT boxes, and either I have not yet implemented the hole punching or it just didn't work. And in that case, they fall back to a relay server that I also run. And that behaves very much like a turn server, if you're familiar with that. It's just gluing two TCP connections to each other. I want to make sure the clients use a direct connection whenever they can, because again, I don't want to foot the bandwidth bill for everybody's bytes in the world. They can always fall back to this. All right, so once that handshake is complete and you have a direct connection to somebody, then it turns into kind of standard encrypted record pipe. This is all using the NaCl crypto library. It's a Python application, so it's using PyNaCl, which is a Python binding to libsodium. All of the messages are exchanged with the secret box, SALSA20, and Poly 1305. The keys are all derived using HKDF from the master key. There's a separate key for each direction. They're using a counter as a nonce. And the data gets hashed as you're sending it over the wire, and then the final ACK says, this is the hash of all the data that I received. Is that right? So this is the kind of normal stuff. This is normal symmetric crypto. And the package includes a library that you can use in your own applications. You make a wormhole object. You say, here's the code that I want to use. There's another function call to say, please allocate me a code. You then give it a record, send data. The other side says, get data. So there's both a blocking style and a twisted, an asynchronous style to this. So you can use it in network applications to use either forms of those. And it handles all the network protocols, all of the encryption, all the stuff that you need there. The next set of stuff that I have on the roadmap, making some better forms of installers, making some GUIs where you can drop a file onto it, where you can double-click it and get back the code, paste in the code, a file pops out. I think turning into a browser extension would be pretty cool. That could be pretty handy. Negotiating better transport, so being able to use WebRTC or NAT, ICE, some of those hole punching things should be in there. Running this as a Tor onion service is also pretty handy because that takes care of the NAT stuff for you. Tor onion services let you bypass that stuff really easily. I'm hoping to try and get the SPAKE2 algorithm into libsodium, where it will be available in a lot of different languages, not just Python, and port it to other languages. Some of this is going to require breaking changes to the protocol, so if you start playing with this, just keep an eye out for updates, and it's quite possible that the version that you install today won't be able to talk that I release next week. I'm hoping to get this down to a 1.0 in about a month or two and have that nailed down. So beyond file transfer, the reason that I'm pushing this is because I think this idea of Pake with a randomly generated token that's single use is a really useful primitive that needs to get out of the kind of academic lab and into industry, into the trenches. This is something that you can use anywhere that you need to deliver a credential to a new machine. So like provisioning a client device. So at the moment, if you have a service and then somebody says, I want to have this app on my phone that talks to the service, and as the author, you're providing the backend service and you're providing the application, and the question is, how do you wire the two of them together? The most common way of doing that right now is to have the user choose a password, and the user tells the server what that password should be, and the server stores that somehow, and then the user tells their device what the password is, and the device talks to the server as if it was a normal user. Passwords, we all know just how bad they are. User-chosen passwords tend to be pretty lousy, pretty guessable, they're forgotten very easily. And this is a case where the device that is trying to claim attachment to a service is much more capable than the human. You know, we could do something much better than just using passwords here. So the technique I'd like to encourage with this library is that instead of typing a password into the client, you go to the server and you say, I'd like to have an invitation. I'd like to add a new device to this thing. And it says, great, here's your wormhole code. And you type the wormhole code into the device. And because it's coming from a well-defined grammar, you know, there's this fixed word list and you know exactly what the shape of it ought to be, you can have much better UI for that. You can have autocomplete. The command line tool does autocomplete on those words once you've typed in the first few letters. You can have, on a phone device, you can do drop-down menus. You can represent this code in lots of different ways. You could have a QR code for it. You could have, you know, something else. There are devices like, I think the Chromecast do some sort of ultrasonic thing where like your phone listens for the Chromecast to send an audio tone out through the television to figure out that they're near each other. There are a lot of different options here. And that code is single use. So, you know, none of the security depends upon that code remaining secret a millisecond after this protocol finishes. So it doesn't matter that it's short, it doesn't matter it gets left around somewhere. Another kind of application for this messaging app, something like Signal will, you know, when Alice sets up her device, she makes a key pair, she uploads the public key to the Signal key servers. Later, Bob comes along and says, I'd like to talk to somebody called Alice, and he points at Alice with a phone number, and the Signal key servers say, let me check, okay, here's the public key that she registered. So Signal is great, they've done a really good job with it, but one of the problems here is that that server is in the position to supply a different key than the one Alice had, and you have to go through this verification process afterwards. I think a lot of messaging pairing applications are much more face-to-face, where, you know, we're meeting here together, and I want to say, hey, let's like exchange numbers. Really, our phones could exchange more than just numbers. They could exchange full keys, and then we're not dependent or not reliant upon servers anymore. So in this application, I would have one of the devices display a wormhole code. The other one, you either type that in, you QR code it, something like that. And then the two machines, you know, Bob's machine gets the key directly from Alice's machine through this wormhole protocol. So the real reason I'm pushing this stuff is because I want Pake to be something that's available in your toolbox. The rate of diffusion of cryptographic tools from the academic world into industry is just abysmally slow. You know, symmetric encryption was first developed in like 500 BC, right? Like Julius Caesar, and it's only been the last like decade that we've thought as engineers and developers, oh, I could totally encrypt that thing. The next batch of stuff that's slowly coming in are like public key signatures, public key encryption, hashing, and even those, like public key encryption is still just kind of on the edge of what we feel comfortable using. Like if you go to your coworkers and say, yeah, we can just like public key encrypt that with this thing, they'll be like, that sounds like a lot of work. That's probably like, do we really care? It's not really something security critical, they're just cat videos. So it takes decades. That stuff was first defined in the 70s, and we're just now being able to use it as a general thing. So I kind of believe that to get one of these techniques out into the world, you need to have some good compelling use cases, you need to have some clear examples, some good libraries, some tools, so that somebody can say, oh yeah, I heard that such and such company is using that technique, or I've seen lots of people doing that, I guess we can do it too, and have it be not so much of a wild, crazy thing that you're going to get looked at funny by your coworkers for. So file transfer is a foot in the door. I mean, getting a file from one place to another is not a very sexy application, but it's a useful tool, and I think it works better than a lot of the other tools we have right now. But it's a foot in the door to allow the rest of Pake to come into your toolbox. So yeah, that's it. Magic Wormhole, moving things from one computer to another safely. Check it out on GitHub, pip install. My name is Brian Warner. You can reach me via email or Twitter, Lothar with a triple R. And I can take a couple questions. Thank you.
Yeah. So there seems to be a denial of service attack.
Sure.
That attacker can cycle all the channel IDs and just spam into those tools.
Yeah. There is definitely a very bad denial of service attack here, and I don't have a good answer for that yet. This is sitting somewhere in between. I think it's really useful up to a certain amount of attention, and maybe beyond that, it becomes hopelessly unusable. You know, you can imagine doing some things where you do hash cache, or you have to get a token from somebody, do some sort of captcha thing before the service is willing to accept that. But that cuts back on the usability quite a bit. So yeah, it's definitely a problem. I don't have a good answer for it. Yeah?
So on your chart earlier, where you compared the various types of transfer, if you were to put WebRTC on that chart, what would it look like?
Yeah, so WebRTC in this comparison it's great that it's built into browsers. It gets you that 80% of the time gets you a direct data connection between the two machines, and the rest of the time you go through a relay server that somebody else is providing. So like Twilio has a service where they'll just take care of all of that for you and then charge you by the gigabyte. The WebRTC setup flow involves the page in the browser saying, hey browser, I'd like to do WebRTC, please give me an offer. And that's basically a Diffie-Hellman message. And then you need to get that message to somebody else somehow. And most of the WebRTC-based video chat applications have the back-end server that's providing the page also be the one that's delivering that offer. And then the other side receives the offer, generates its own offer, sends that back up. So it's the moral equivalent of unauthenticated Diffie-Hellman. You could use this to get that offer protected from one side to the other. And the property of WebRTC is that the offers don't have to be secret, but they do have to be authenticated. So it would be a little bit overkill to send these through Magic Wormhole, but it would give you the authentication process that you want. There are some other protocols that might be more appropriate for that. There's one called short authenticated strings, which is what you can do after the fact. So you make the WebRTC connection, and then you verify that you both did get the same offers and you have the same session by doing some other exchange between the humans. The big trick of all of that, though, is that there are two different things you're trying to do. One of them is you're trying to as a human, you're telling the computer, I want to talk to that computer over there. So you need to point to somebody. And then you also need to verify that you wound up talking to that particular machine. And the order of operations becomes significant. So if you did the WebRTC thing, at the beginning of the process, you have to somehow say, I have this offer, how do I get it to that human that I want to have type it into their computer? So you have to like point in the beginning, and then after the connection is finished, you have to do this additional verification step. So there are two phases. And the thing I like about the PAKE approach is that at the beginning of the process, you get this token that you have to give to somebody, and in the same step, you give it to somebody and you get the arrows are both pointing in the same direction, so you can use a single message to send both, if that makes sense. More questions? Yeah?
Do you support
parallel TCP DMs for data transfer? Not yet. Part of the compatibility breaking changes I want to put in here is to allow the two sides to evolve their connection over time. So they start saying, try connecting to this. If that doesn't work, let's try this, let's try this. And as the sides discover more options, like if they're spinning up a Tor onion service, that may take 25 seconds to get set up. They can start by saying, try doing this, and then 20 seconds later, oh, now there's this new thing that might be cheaper, it might be more reliable. And I think that parallel TCP streams could fold into that, where we say, hey, I've just discovered I have multiple pathways out to the internet, I could merge them together. And then the encrypted record protocol here is basically saying, record number 1, record number 2, record number 3. So there's some nice framing information there that it could use to interleave that between multiple streams.
kind of like purification on the layer above natural secret box? There's like, that's supposed to be like a replacement for SSL, but there's a big gap.
Yeah, Yeah, so verification on the layer above NACL secret box. Not a lot. I've got that hash check, so that basically at the end of the process you can discover if something went wrong. The things that could go wrong, if a record were dropped, then the counter would notice that. If the key was wrong, then the initial key exchange should have failed altogether. So that's really guarding against memory corruption, or something in your decryption routine went bad on a particular packet, something like that. Maybe like a zero-length packet that confused it. Yeah. Any more? Okay. Oh, one more.
Oh, yeah.
One more.
So this is really useful for synchronous exchange between
Yeah.
Like email is great because it's asynchronous.
Yeah.
Is there anything in your mind like that led you toward the asynchronous solution?
Yeah, so synchronous versus asynchronous. This is very much about something interactive, and the security properties you get out of it are because of that. So one thing I'm looking to use this for, I am working on an encrypted messaging thing called pet mail that's much more email-like. Adam Langley's Pond has this thing called Panda that goes along with it, which has a very similar need, where you want to be able to meet here when we don't have our computers, agree upon some string, go back home, type that in, and then have the computers get joined up. And you can do that with this. You can choose a wormhole code out of band and just type it in to both sides. But the two machines need to be doing that in some overlapping period. And because they exchange, 3-4 messages, you need to have them both online at roughly the same time to be able to complete this in a reasonable amount of time. It's worth noting that you can say wormhole send -- text and a string, and that doesn't use this transit server at all. So then it only has to exchange 2 or 3 messages. And you could even have it, I'll turn my computer on now, I'll turn it off. Tomorrow you turn yours on, you turn it off, then I turn mine on, and after a couple of days it'll finish with that. But I really think this is most useful in a setup phase, where you do this to get those two machines to know about each other's keys and about how they can route messages to each other, and then you have something else that does the more asynchronous kind of stuff.
It'd be great if everyone has their phone in all the time, right? If we just say everyone put their app on their phone, the phone does the key exchange, you can just tell the other person you have the phone. And
Yeah.
if I'm talking to a computer and finish the exchange,
I definitely believe in we have these user agents that we carry around with us all of the time, and our user agents can talk to our other user agents. So when we meet in person, now our phones know about each other, and we go home and my phone knows about my computer and your phone knows about yours, and therefore the computers can be introduced through the phones. That is where I'm pushing with most of my other tools. All right, cool. I'll be around all night if you guys have other questions. I think we'll get the next speaker up here. Thanks very much.
All right, thanks again, Brian. Looking forward to magic wormholing some files to people.